Welcome to the lecture series on deep learning in artificial neural networks. In this video, we discuss the loss landscape, in particular the configuration of minima and saddle points in the loss function. When we change the weights by gradient descent, we walk along the loss function. Here's a typical hand-drawn graph. We have really good minima. We have minima which are nearly as good, and then we have local minima which are considerably worse. Now, this is a hand-drawn graph. We plot it as a one-dimensional function of one parameter, and this one parameter would be one of the weights. For example, it could be the weight from neuron J to neuron I in layer N. But there are many of these weights. Minima are characterized by the condition that the slope is zero. So down here, it's flat. Here it's flat. Here it's flat. The derivative is zero. So minima are characterized by this zero derivative, but so are maxima. So what's the difference between a minimum and a maximum? Well, at a minimum, if we come from the left-hand side, we first have a slope that is negative, then we have slope zero, then we have a slope that is positive. That means the second derivative of the error function as a function of this weight W8, WA is positive. For maximum, it's the other way around. The second derivative is negative, and occasionally we also have plateaus where the derivative is zero. So I would call this a plateau. So this was a plot in one dimension. In two dimensions, it's a bit more complicated because it's possible that the second derivative is negative in one direction, yet it's positive in the other direction. And then this is a point called saddle point where the derivative is zero, but it's a minimum in one direction and it's a maximum in the other direction. I don't really like these 3D graphics. I prefer to work with niveau lines. So it's here again two weights. We have picked out two of these parameters, WA and WB. And then what we have here are niveau lines, lines of equal loss. And here, at this point here, there would be a minimum, and then here would be another minimum, and here, this point here, that would be the saddle point. So if we walk down, starting here, then we move first in direction of the saddle. And at the saddle, because we are a little bit on the lower side, we actually will turn around and then we go towards the minimum. If we started on the other side, we would again turn around, but then go to the other minimum. In the 3D graph, again, here we go down close to the saddle point. The movement is very slow. The gradient is very small. At the saddle point, it's zero, but we are never exactly at a saddle point. We then turn around, and in this case, we would go down to the minimum that's somewhere on this side here. So in this configuration, we have two minima separated by one saddle point. And now, in order to strengthen your intuitions, I would like to ask you how many minima and saddle points are there. And we will consider a network with 9 layers and 10 neurons in each of the layers. And here's a proposition. A deep neural network with 9 layers and 10 neurons each has typically between 1 and 1,000 minima. We have seen there could be global minima, there could be local minima. Do you think that this is correct? Or do you think it has typically more than 1,000 minima? Again, global or local. And I remind you, You may pause the video before we continue so that you can really think about this and make your own estimation. And here's the answer. Yes, it's more than 1000 minima. That's a lot. We have only 9 layers of 10 neurons each and more than 1000 minima. Okay, how much more? How about this? It has typically more than 1,000,000 minima. Well, that sounds a lot. Do you agree? Well, this is still true. Well, then let's get really crazy. How about this statement? A deep network with only 9 layers and 10 neurons each has typically more than 10 to the 20 global minima. Do you believe that this is true? And yes, this is also true. So far for the minima. Now let's look at the saddle points. We again have 9 layers, 10 neurons each, and the question is, so we have seen there are many minima. There's many minima. In addition, a few saddle points, or about as many saddle points, or even many more saddle points than minima. Again, make your decision. And the last option is the correct one. So there are even more saddle points than minima, and we have a huge number of minima. And all of these here, I only counted the global minima. So in the following slides, I would like to explain where this huge number of minima comes from. And essentially, it's due to permutation symmetries. There are symmetries in the space of weights, in the weight space, which leads to a huge number. And this number is that they are at least n factorial to the power of m equivalent minima. So in our case, our assumption was we have 10 neurons per hidden layer. So this makes 10 factorial. And then the whole thing is to the power of m, it's to the power of 9. So the 10 factorial gives in a range of 1,000,000, it's larger than 1,000,000. And then the whole thing goes to the power of 9. So this is more than 10 to the 50 minima. So suppose you have found one global minimum, then in fact this is just 1 out of 10 to the 50 equivalent minima. An immense number. So let me try to explain this. So here I have a network which has 4 hidden neurons, and this one neuron implements this hyperplane here. The second neuron implements a second hyperplane. The third neuron implements a third hyperplane, and the fourth neuron implements the fourth hyperplane. Now, we could say the first hyperplane is implemented by neuron number 1, and the second by neuron number 2, and the third by neuron number 3, and the fourth by neuron number 4. But we can also say the first hyperplane is implemented by neuron number 3, the second by neuron number 4, the third one by neuron number 1, and the fourth one by neuron number 2. And so in total there will be many permutations. In fact, for 4 neurons in one hidden layer, there will be 4 factorial permutations. So now let's continue with the second example. Now I have a 3-dimensional input space, and let's suppose that all the positive examples lie inside this blue box. Then I will need 6 hyperplanes to characterize this blue box, and I can implement this by 6 neurons. But it's not that because I'm now in 3 dimensions that the number increases. Also in just 2 dimensions, 2 input dimensions, if I have 6 hidden neurons, I could use those to implement a more complicated function. So this is my 4th hyperplane, this is my 5th hyperplane, and maybe this is my 6th hyperplane. And so I could separate this kind of space against the rest with all the positive examples lying in here. So with 6 hyperplanes representing the 4 hidden neurons, I have 6 factorial combinations to delimit the same space. So it's really the number of hidden neurons in a hidden layer that determines the number of permutations, and with 6 hidden neurons I have 6 factorial permutations. So far I have focused on the best minima, and the nice way to think about this, about these global minima, is to say, well, the labels are actually generated by a network that has exactly the same number of neurons as the network I will use to learn. So suppose I have a teacher network which generates the labels with a certain set of weights, big W in the first layer, big W in the second layer. And this is how my database is defined. And this specific teacher network used these 4 hyperplanes to delimit the space of positive examples. And now I want to learn this with a network that's called a student network that has exactly the same architecture. It has exactly the same number of hidden neurons. It uses the same inputs, but the weights, small w in the first layer, small w in the second layer, are unknown. And these are the weights we want to learn. And then by construction, because I have 4 hidden neurons, I have 4 correct hyperplanes, I will have 4 factorial different solutions that are all completely equivalent to my teacher network. However, normally data does not come from a teacher network. So in our example with real data, with cars versus non-car, data lies somewhere in this high-dimensional input space. And now I could use 3 neurons to delimit this, but if I have 4 hidden neurons, I could use the 4th neuron once to cut this angle. But I could also use my 4th neurons to cut the other angle. Now these 2 solutions, they are nearly equivalent in quality. However, turning this final hyperplane from this position to the other position will go through positions that are not as good. So these 2 near equivalent good solutions are separated by a saddle. They form separate minima. And now if you think that you have 8 neurons, you could construct even more equivalent, very good solutions. So this number of minima is not just the number of permutations constructed from perfect global minima, but in addition, they are also near equivalent, reasonably good solutions. So let's finish with a quiz. A deep neural network with many neurons has typically many equivalent solutions. And these equivalent optimal solutions all have exactly the same loss. They have the same error value. And of course, this is correct. And a deep neural network with many neurons has typically many near optimal solutions. And yes, this is also correct.